In this video, we're going to talk about line integrals of scalar functions. And that will be the case where you have a line integral like this. In 2 dimensions, we have a function of x and y. Or in 3 dimensions, we have a function of x, y, and z. And you have like ds here at the end. And you're integrating over a curve C. This is the curve over which you want to do the line integral. Now, it's often been pointed out that line integrals is a misnomer because we're actually usually integrating over curves, not lines, but that's the name that we've been given, so we'll go with that. So now when we do this, we evaluate this the above by doing this. So if you're given like one of these line integrals, you're actually going to evaluate it by, and I'll explain in a second what these all mean. Like this, where now R of t is a parametric representation of the curve. So this is how we evaluate like these integrals up above here. We'll represent the curve C parametrically by R of t. Then we'll substitute R of t in the function, could be a function of 2 dimensions or 3 dimensions. Then multiply this times times the arc length of the curve and dt. And I'll show you in a minute a basic example, and you can see how this all works. So let's take an example like this. Evaluate the line integral. Let's say xy. Let's say 2xy minus 3y squared ds, where c is the curve represented parametrically by R of t equals 2t to the 4th minus 3t to the 4th, like this. So let's say we're given this line integral. And now again, the parameterization of the curve has already been given to us. later we'll do some examples in which this is not given to us, but right now for this one it is. Also, for this problem here, we have to be given the range of t. Here, t, it varies from 1 to 3. I didn't write that down originally, but t is varying from 1 to 3. We'll need that when we do the line integral. So again, what we're given here, we're giving an integral in this form here. So we need to identify what our function f is. So our function f(x,y) is this function right here. And that's what we're going to substitute our r of t in a minute. So in this case, our function f of xy is 2xy minus 3y squared like this. And then we're going to substitute r of t into that. What I'll do, I'll substitute into our function first. So again, our function is this right here. This is going to be our function, f of xy. And according to what we have up here, we want to substitute this into our function. And so that means wherever x appears, we're going to put 2t to the fourth. And so up here, we're going to put 2t to the fourth. Wherever y appears, we're going to put minus 3t to the fourth. And so again, I substituted up here for x, put in 2t to the fourth, y minus 3t to the fourth, then minus 3 times y squared. So and substitute for that. Like this. And we can simplify this a bit, can't we? We can say, let me move this up a bit here. We can say that 2 times 2 is 4, times 3 is 12, and then with a negative, -12. And then the powers, we're multiplying the t, so we're going to add the powers. That'd be t to the 8th. Over here, there's a -3 times -3, which gives us a +9. Excuse me. We're squaring this first. So we're going to square this. So it's going to give us a +9 when we square it, multiplied times a -3. So it'll give us a -27. And then this is t to the 4th squared. That'll be t to the 8th. And actually, this one simplifies real nicely. This is going to be minus 39 t to the 8th. So that gives us our function with r of t substituted in for x and y. And let's take a look at what else we're going to need. If you look back at our equation, we're going to also need the derivative of the parametric curve and take the magnitude of that. So let's go ahead and take the derivative, and that will be the derivative of this over here. Let me just write the original down so we can kind of have these side by side. Since this is a vector, I should represent these by angle brackets. I fixed these over here. And so this is going to be r t to the fourth must read t to the fourth like this. And then take the derivative, because that's what we're going to need for our equation. So again, take the derivative of each of these with respect to t. This is going to be 4. That's going to be 8t cubed. This is going to be negative 12t cubed, like this. And according to our equation, we're going to need the magnitude of that. That'll be the square root of the sum of the squares. Like this. And this is going to be the square root of 64. When we square, then this will be t cubed raised to the second power. So it'll be t to the 6th. Then this is going to be 144. That'll end up being positive because we're squaring it. And then same thing here. This would be t to the 6th. And we can actually what we can do, we can factor out the t to the 6th, the square root of that. And then if we add these together, what is that? 208. And of course, t to the 6th, square root of that is t cubed. So let me put the number up front. Square root of 208 times t cubed. Like this. Now we have everything we need to substitute into our integral, because we have our function with the parametric curve substituted. That was minus 39 t to the 8th. We have the magnitude of the derivative of our parametric curve. So we can just substitute everything in. In fact, let me kind of write that down, what we're actually doing here. So we're doing AB. And we have this here. And we're integrating from 1 to 3 because our value, I forgot to mention that previously. Hopefully I put it on the a note on there. This curve is going to be from t equal 1 to t equal 3. That's something that has to be given to us to be able to do the problem. We have to know what the range of t is, and that's going to be the bound of our integral. So in this case, since t was going from 1 to 3, then we'll put that as our bounds. And then again, our FR of t was what we found over here. Negative 39 t to the 8th. And then our magnitude of our R prime t was the square root of 208 t cubed dt, like this. And of course, we can always pull our constants out front, negative 39. And since the square root is not a perfect, the square root is not a square root of a perfect square, we'll just keep it there. And then we'll put these together, t to the 8th times t cubed is going to be t to the 11th. Like this. Then we'll go ahead and integrate. This minus 39, square root of 208, 12th. Put the upper bound in. Now we could have separated these, which would make it a little bit more compact, but I'll show it this way so nobody gets confused on that. And then we have these numbers. And I put the 3 to the 12th divided by 12 times 39 into my calculator and got this. And then I took a negative becomes a positive. 39 divided by 12 is going to be 3.25. Of course, 1 to the 12th is just 1. And then finally, when you multiply this out, you get negative 24,909. 744.21, like this, or negative 24.1 times 10 to the 6 would be a simpler way to represent that. And so that's the line integral. Next, let's take a look at this problem. Evaluate this line integral 2xy minus 3x ds, where C is the line segment beginning at the point minus 2, 5 and ending at the point 4, minus 7. Now, unlike the last example, this time we're not given the parameterization of the curve, though we're told it's a line segment beginning at this point and ending at this point here. But so you recall, we learned previously how to parameterize line segments. You recall, first of all, we kind of need like a direction vector. Let's call this V. And it'll be directed from this point to this point. So you remember how we did that. We'll take the second point and subtract the first point. Get our direction vector. This will be 6 minus 12. And then for our parametric curve, we can use V times T plus rho naught, where this is rho naught is the very first point in the form of a position vector. So we'll just write this as 6 minus 12 T plus this, again, the first point has to be the first point. like this. Then if we multiply these out, this will be 6t minus 2. And this over here will be minus 12t plus 5. And that's going to be our parametric curve, though in this case it's a line segment. And remember, when you use this method, it automatically works out that this parameter t will go from 0 to 1 if you follow this method here in this equation. And let's just double check. When you put in 0, if we put 0 here, we'll get -2. If we put 0 here, we'll get 5. So that's a position vector pointing to our first point. And then if you put 1 in here, this will be 6 minus 2, which is 4. And then if you put 1 here, this will be minus 12 plus 5 minus 7. So that gives us a position vector to the second point. So this is our parameterization. So next thing we have to do, we want to identify our function. And so our function here is going to be fxy is going to be 2xy minus 3x, like this. And then remember, when we're using our equation, we're going to need f of rt. And so f of rt means that we're going to put these into our function. Remember, this is the x coordinate. And this is the y coordinate. So I just put x into here, y into here, then minus 3x. Once again, put this in for x. Like this. So I went ahead and multiplied these. I FOILed these. And I got 6 times 12 is minus 72. And 6t times 5 is 30t. 2 times minus 12 is 24t. 2 times 5 is minus 10. Then multiply these out, minus 18 plus 6, like this. And let's go one more step here. Let's do, multiply this up, minus 144 t squared plus 60t plus 48t minus 20. And over here, let's put this minus 18t plus 6. Now let's combine as many terms as we can. So we can put the t's together. And that'll give us 90t. We put these 3 terms together, then the constants, that gives us minus 14, like that. And once again, looking at our equation here, we're going to need r prime of t. And over here we had r of t with this. So let me just write down the derivative of that. And so again, let me just write down what we originally had just for clarity. We had 6t minus 2 minus 12t plus 5. And of course, remember that is going from 0 to 1. So we'll take the derivative of this. Of course, that's pretty clear cut what we're going to get. It's just going to be 6 minus 12. It's actually going to be that direction vector. Again, that'll be true if we have a line. In general, that's not going to be true. But so we have just that direction vector for the derivative. And then we're going to need the magnitude. Like this. That would be 36 plus 144, which is the square root of 180. And now we have everything we need. We can substitute it into our equation. Let me just write down the equation. And then substitute everything that we had. We found our FR of t here, which is this. And then we have the square root of 180 here, dt. Again, remember we're integrating from 0 to 1. And we can bring the square root of 180 in front. And integrate, that's going to be 144 t cubed divided by 3 plus 90 t squared divided by 2 minus 14t 0 to 1 like this. Then we're going to have, so it's going to be 180. And of course, 1 cubed is going to be just 1. So I can just make this 144 over 3. And that's going to be 1. And that's going to be 45 when we divide 90 by 2. And then this would be 14 times 1 with that. Now notice the lower bound has just t's in it. And so it's going to be 0. You always have to be sure to not automatically put 0 when you put a lower bound. And always take a quick look at, be sure to have, because remember, if we have like e to the t, e to the 0 is not 0. So, but in this case here, these are all going to be 0. And so again, when we reduce all this, this comes out to minus 17. And then over here, of course, that was already 0. If you put this in your calculator, you get something like minus 228. I'll round it off 0.09, like that. So again, just like the last problem, we used this equation right here. But this time we had to make a parametric representation of our line, and we did that. And then just plugged everything in and calculated it out.